Welcome to the Rich Report, a podcast with news and information on the world of high-performance computing. Today, my guest is from Convey Computer. We have the president and CEO, Bruce Toal. Welcome to the show today.
Hey, Rich. Good to talk with you and your listeners again.
You bet. It's great to have you back. And I thought we'd just go through your slides today and follow that with a Q&A. So, Bruce, I brought those up if you want to get started.
Great. Well, what I wanted to do is share that we've announced a new product and tell you a little bit about that. So the first slide, kind of, what is I'm going to tell you. First, I'll do a little review about our products, and we call them hybrid core and what that means. And then I'll talk about what's new about the product we're introducing. And of course, it wouldn't be called high-performance computing without some notion of what the performance would be. And then I'll just kind of summarize. And let's move to slide 3. So what is hybrid core, or what does it do? So what we set out to do was deliver higher performance for application-specific computing. And we deliver anywhere from 5 to 25x on the application domains that we focused on. We'll talk about that a little bit later. And that yields huge power savings. We've got an example later that we'll talk to. And our background coming from convex, HP and whatnot is, we understand that just having a fast box that's hard to program is not very appealing. So we strive to use things that make it easier for people to program and manage our systems. And then there's just a little quote there from one of our bioinformatics customers. Let's move on to the next slide, number 4. So kind of simply, what do? We start with using Intel x86 processors, and our view, and I think most would agree, is it's a dominant server architecture today. And we add field programmable logic, and we use this for application-specific acceleration. And we have the compiler team that we've had going back to our convex days. So we deliver C, C++, Fortran, and other performance libraries such that it's easy to use the accelerator. And we put this on a standard OS, so we use CentOS, Red Hat derivative. And of course, the goal is to lower costs, save you power and cooling expense, and deliver performance. So let's take a look at the new product, HC-2 and HC-2X, 2EX. Very creatively, we're following that. It's the new product follow-on from the HC-1 and HC-1EX. So the platform delivers 2 to 3x more performance over our previous generation. And of course, binary compatibility is one of our mantras. So you don't have, our platforms are completely open. We have people developing applications themselves. We develop applications, so it's important to be able to maintain programming models as you move from platform to platform. So the HC-2 also includes the latest generation of x86 host servers. So we've been shipping now the Westmere genre, and we're also going to be shipping the Sandy Bridge genre servers here shortly. So we're announcing basically in all of those platforms, today as the host servers for our overall system. And we've added more manageability features around redundant power. And then, we coined a new term just to make things, more, clear or challenging, whichever your view is. We call it our hybrid core memory interconnect. So the way we attach the processor is via PCIe to the coprocessor. But we do that in the fashion which preserves the programming model that we've always had, which is a globally shared virtual address space. So moving to slide 6, let's take a look at the architecture of the HC-2. So we've got an x86 host, and we've coupled that to the FPGA coprocessor, as I mentioned, using PCIe. The key thing here is that we support a globally shared virtual memory, and that all that. If you look in the coprocessor side down on the memory section, the memory controllers that we've engineered to this coprocessor. There are 16 DDR2 DIMMs attached to those memory controllers, and they do all the virtual to physical translation. So the coprocessor deals completely with virtual address spaces. So whether it's the memory is physically local to the coprocessor or on the x86, that all gets resolved in the memory system. So preserving that single process, single address space programming model. Another really cool thing about what we've done with the memory system is this memory system is scatter-gather, and which means this is a terminology us vector guys have used and implemented a lot over the years. So we don't have any caches on the coprocessor, so that means that on every clock cycle we can access an 8-byte quantity of memory, and without having to worry about waiting for a complete 64-byte cache line coming back. So in the case of a lot of applications that simply need one out of the 8 words of a cache line, you have 8 times more efficiency in your memory system. Plus, it's an 80 gigabyte per second memory system, so lots of bandwidth, and perfect for things like sparse matrix or table toy chasing, pointer chasing, those type of applications. Okay, so let's move to just a quick comparison here of the HC-2 versus the HC-1. So we've already mentioned 2 to 3 times more performance than the previous generation. We use the latest generation of x86 hosts, so both Westmere and Sandy Bridge. We've got a number of configurations that can be supported, and you can put a lot of memory in these platforms. Serviceability, so we're a big believer in our users being able to put these in data centers and do remote monitoring, remote booting, and that they be reliable. So it's got features for enterprise computing around redundant power and remote monitoring. And of course, we've touched on compatibility, binary compatibility as well. All right, so let's get to the performance aspects. So here's a Burrows-Wheeler alignment performance chart. And this is simply when you take a piece of genetic material and you run it through one of these sequencers, you'll end up with billions of reads, they call them. And these reads are, the next challenge is it's a puzzle to take these billions of reads and align it to a reference genome, and that's what this application does. Our HC-1 was doing that at about 2.5 times what a 12-core x86 was doing at about 7,000 reads per second. The HC-1EX was doing it at 27,000 reads per second, and the new product we've introduced here is the HC-2 does that at about 67,000 reads per second. So overall delivering just under 10 times more throughput than an x86 platform. Next slide 9 is where we'll look at BLAST, also a bioinformatics app where this illustrates that our HC-1EX was getting about 21,000 seconds of elapsed time to do this particular alignment. And the HC-2EX, the far right there, is getting 540 seconds, so 4x more the performance with the new platform. So what does that mean? So let's look at slide 10 that looks at the economics of this. And so this is a Smith-Waterman search, another bioinformatics example. And not going to cover it all here, but we look at all the aspects of how much does it take to power all these the different pieces of how much electricity costs, and then in the end, the last set of numbers on the left-hand side is the 3-year total cost of ownership. And the comparison here is of 8 Convey HC-2EX platforms, racked, as you can see pictured over to the far right, and compared to to get the equivalent level of performance, you're looking at 117 12-core servers, so 3 racks of equipment to do that. And so that translates into less than $1 million for our systems to do that versus a little over $3 million of total cost of ownership for a kind of standard x86 cluster there. So in the bottom right in the purple there, you'll see overall some very impressive reductions in floor space, power, and 3-year total cost of ownership. 75 to 80% reduction. Okay, well, I'm going to wrap up here with just summarizing. So the HC-2 is 3x the performance of our previous generation, and anywhere depends on the application, 10 to 50x over a standard commodity server. We brag about its flexibility in terms of price performance. Programmability is, I think I've touched on that a lot, and that's because we're pretty passionate about it. So I'll stop there, Rich, and turn it over to you.
Well, great. Well, thanks for that, Bruce. Say, I'm curious about the HC-2, the way the memory works. I mean, do you have a shared memory space across physical boxes, like a global SMP kind of thing going on?
Yeah, so we actually tightly share the two, we'll call it processors. A coprocessor, plugs into the server via PCI, and that memory is globally shared virtual space between both of those compute systems.
And is that NUMA? Is it non-uniform kind of memory access?
Yeah, exactly. Good question.
Yeah.
So it definitely is NUMA, and all the standard, we'll call you can say advantages or disadvantages of NUMA apply here. As you compute best when you have memory closest to the processing element. But the beauty of this, in terms of the programming model, is when you reference memory that's attached to another computing element in CC NUMA fashion, you don't have to do an explicit move operation. It just happens automatically, through the standard virtual memory system.
Sure. And have you had some genomics type customers, with beta testing this stuff? And if you did, what kind of results were they getting?
Yeah, so the Jackson Labs has had a system. They were the first ones to get an HC-2 back in March, and they're using it to do Burrows-Wheeler alignment, and they're getting over 10 times the performance of what they were getting with their previous just x86 only platform, and they're just thrilled because they're able to now do their searches in considerably less time and be more productive.
And are you guys on the Sandy Bridge? I must have missed that. Are you getting up there with the new processors, and does that help as Intel ramps up?
So the performance is mileage varies as you know in this industry. So there are areas where Sandy Bridge performance helps. There's areas where just Sandy Bridge SKUs are more cost effective. So so we'll actually start shipping Sandy Bridge product. It's in the lab and going through final validation, safety testing, and whatnot. We'll ship that later in Q2, and we're already been shipping Westmere-based platforms.
Oh, great. So, Bruce, kind of a wrap-up question. Does this new memory architecture, is this the foundation of a kind of a new path for this architecture? And I mean, how would you see customers benefiting from that? Is is it a programming ease kind of thing, or what do you think?
It really translates into performance. So when you and I had a podcast about this time last year, when we were talking about Graph 500 performance,
yeah,
what we've been able to achieve with just a single one of our platforms, was equal to what was being delivered by some pretty large XMT platforms, or even the Jaguar system at Oak Ridge. So just phenomenal performance when you've got applications that are using, can take advantage of that scatter-gather type of memory access pattern.
Well, terrific. Well, Bruce Toal, I want to thank you once again for coming on the show today.
Always enjoy it, Rich. Take care.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.